Welcome back. So today we're going to start moving into a new area of quantum mechanics. So for the last few weeks, we've really been focusing our attention on spin and developing the idea of Hilbert spaces and what it means to be an observable quantity. And today we're going to transition into sort of a part of quantum mechanics that asks questions about what happens to states really as we translate them, right? As we're moving them around. And as we do this, we're actually going to start using one of the big equations of quantum mechanics, but I don't want to get ahead of myself because before I tell you what this equation is, I want to tell you why you probably already know what this equation is, right? So back when you studied special relativity, you knew that there was something about the energy of a particle, right? After all, the energy appeared in the time component of the form momentum, right? There was something about the energy of a particle that told us how that particle moved through time, right? And that's the big idea that I want us to remember today, is that we have some intuition for the fact that energy corresponds with moving through time, right? That energy is something that generates, shall we say, movement through time, and we saw that again explicitly in the 4-vector when we were talking about it in special relativity. So energy determines time evolution. And if you buy that, right, or if you remember that or something, then it's not too big of a jump for us to look at the Schrodinger equation, right? The equation that we know really everybody talks about when they talk about quantum mechanics. And what the Schrodinger equation really says is that the time derivative of a state, right, and of course time derivative tells me how is that state changing. Well, that state is changing because of the right-hand side of this equation, which is the operator known as the Hamiltonian. Okay, and the Hamiltonian, if for some of you are taking classical mechanics, the Hamiltonian is an operator that talks about the energy, right? So the Hamiltonian is a fancy word for the energy operator, and maybe to be more technical, the Hamiltonian is the operator that asks, hey, what's your energy, right? And then the energies are the possible measurements of the Hamiltonian, right? They're the eigenvalues of the Hamiltonian, and they are the things that correspond to each of the eigenstates or eigenvectors of the Hamiltonian. And so what this says is that if I can decompose my state, right, or if I apply the Hamiltonian to my state, I get out information about the different energy states of my system. And the different energy states of my system are going to determine how my system propagates through time, right? And now I want to tie this into what we talked about in the last video, because this idea of using an operator, like the energy operator, which is absolutely, by the way, a Hermitian operator, right? Because energies are real measurements. If I have a state, or if I have a pure state of the Hamiltonian, I'm talking about measuring an energy, right? This is something that we've done a lot in physics over the last couple of years. But if I want to think about using or recasting this in terms of a unitary operator, that is, or recasting it in terms of what does it mean to take my state psi and move it a little bit forward in time. So here I'm taking psi of t and I'm adding a little bit of delta t to it. Well, I know that I can approximate that as long as delta t is small, right? I can approximate it as my initial state plus delta t times the derivative of the state. This is just the Taylor expansion, right, through time. Well, I can use the Schrodinger equation to replace that derivative with time with the Hamiltonian, right? And I can now take those two terms, pull them together into hard brackets, and this is exactly what we saw last week when we were building unitary operators from Hermitian operators. And so this expression that we have here, which we generated just by thinking about moving my state a little bit forward in time, right? So just using, having some infinitesimal transformation through time, I found that is the prime generator for an actual operator that's going to allow me to move through time over some finite amount. But at this point, this is really just a way for us to remember or see or think about how the Hamiltonian now, the energy operator, is really the thing that generates time translation. That the ability to go from one moment in time to the next sort of requires us to ask the question, hey, what's your energy, right? Because it's those states that are going to evolve through time, and probably because we're seeing this in a quantum class and we're thinking about states by states, each of these energy states might evolve through time slightly differently, right? So that's where we're going to have to end up with this. So if I take that infinitesimal operator and I promote it to the finite version, right? So now I'm calling my propagator through time, or the time evolution operator. I'm going to call it capital T, and in parentheses, how much time are you evolving? And so I'm going to call it delta T for most of this video. Well, I know I have to, I go from that last slide, I have to exponentiate minus I over h bar times the Hamiltonian times how much time has evolved, right? This is an expression. And this is a beautiful expression, although it is admittedly one that's hard to parse in this particular language. And that's because if I don't know what the Hamiltonian looks like, right? If I don't know what the dimensionality of the system is, there's not much I can do with this time evolution operator, right? We know that we can write down this beautiful, I'm going to exponentiate a matrix thing, right? Or sometimes it's not even a matrix, right? In sort of the discrete and finite size Hilbert spaces that we're dealing with, then it's a matrix and I can exponentiate it. But man, it's going to be hard to think about how could I write this down any better unless I had a concrete example, right? Or unless I knew what the Hamiltonian of the system is that I'm talking about. But nonetheless, I still know that this is going to have some properties that are going to be common no matter what the Hamiltonian looks like. Namely, I know that my propagator through time is going to commute with the Hamiltonian, right? Because no matter how I think about that, e to the Hamiltonian, right? That's going to be some Taylor expansion. It's just going to have copies of h. The Hamiltonian is the only operator that's floating around. And therefore, no matter how many copies of h I have, it's always going to commute with h. And so if I have a pure state of the Hamiltonian, then I'm going to have a pure state of the time evolution operator, right? The Hamiltonian is going to tell me that I can propagate through time. Which means that I'm going to have the same eigenstates. That is, the eigenstates of the Hamiltonian are going to be the eigenstates of the time evolution operator. And if I know those states, then I can propagate them through time. However, my time evolution operator, although it shares eigenstates, does not share eigenvalues. And what's worse, the time evolution operator is a unitary operator, not a Hermitian operator, and therefore it will not have necessarily ever real eigenvalues, right? It will have eigenvalues, and those eigenvalues will help me to propagate the state through time, but those eigenvalues are not guaranteed to be real, and in fact, they're never real. They're never purely real. They're not always real. They might be real from time to time. Anyway. So let's try to do this as generally as we can, and I think I can argue for these couple of steps if I only assume that I have a discrete and finite dimensional Hilbert space. In that case, I can take my general state psi and I can break it down into the eigenstates of the energy operator, which I'm going to call E sub I. So the E sub i's are the states, the eigenstates of the energy operator. And I'm also going to use the same E sub I, but not in a ket. The E sub I outside of the ket is going to be the eigenvalue of the energy operator. I can then multiply, I know that each of those states is going to have a probability amplitude, which I'm going to call alpha sub I, and so I can recreate my entire state by taking alpha sub I times E sub I. Then I want to apply my time evolution operator, right? I want to ask the question, what's going to happen as I move through time, right? And so that means taking this exponentiated Hamiltonian and multiplying it on the left-hand side of my state, right, to allow it to move through time. And as it stands, this is something, again, that's hard to picture unless we know really what it is. But I do know that if I've chosen H to write down in its own basis, right? I don't, again, this is a little hand-wavy because I'm not writing anything concrete down. But if I've chosen to work in my own basis, right, or if I've chosen to work in the basis of H, then H is at least diagonal. And I don't know how diagonal it is, or how big it is, or how many eigenvalues it has, but I do know that diagonal matrices are something that I can apply over and over again. Right? I can do matrix multiplication on a diagonal matrix somewhat easier, and so I can actually take that diagonal matrix and put it into the Taylor expansion and show that I can get out the exponentiation of e to the minus I over h bar times the eigenvalue of the energy for each of the states along the diagonal. Okay? This is going to take a little bit of time to sink in, and it's something that you're going to have to do, right? And in fact, it's something you will do this week on your problem set. But that you want to make sure you're convinced that for this particular form of a Hamiltonian in a particular Hilbert space, where I'm working in my own basis, right, lots of caveats here, that I can write the time evolution operator as a diagonal matrix where the entries of that diagonal are these complex exponentials. And each one of those has a different eigenvalue of the energy associated with it. And now you can see why a couple of minutes ago I said, oh, these are never going to be real. Well, they're always going to be complex exponentials. And so, yes, there are moments when they're real, but they're really spinning around the complex plane, right? They're really, there's something that's moving around as time goes on. And I notice here that when I prepared this, I forgot to add the little delta t's in here, and so I'm going to make sure to include those. I think they appear on the next slide. Okay, so this is what the matrix is going to look like, and I lied, they don't appear on the next slide, but I'll put them up. Okay, so now I'm going to replace that. I'm going to replace the e to the h with the matrix that we've argued is a matrix representation of this Hamiltonian, which means that I can explicitly do my matrix multiplication out, right? Because my e sub I kets, the eigenstates of the energy operator, are just going to be the 1, 0, 0, 0, and the 0, 1, 0, 0, 0, and the 0, 0, 0, 1, and that's boring. But I can now match up, right, these eigenvalues, and I can say that state E sub I, which has energy E sub I, is going to have an eigenvalue of the time evolution operator that's equal to e to the minus I E sub I over h bar. And it's good that I wrote that down because there are two e's, there are two i's, and none of them mean the same thing. But that's the coefficient that gets added to each of the energy eigenstates, right? And so if I was in a pure state of the energy operator, if I was in a pure state of the Hamiltonian, then I would know exactly how the state was evolving through time, right? It would have this phase that's spinning around as time goes forward. But if I have multiple states, right? If I'm in a mixed state, not a pure state of the energy eigensystem, then all of my states are evolving through time, but with different frequencies, right? Because they're moving through the complex plane proportional to their energy. Okay, and that should bring up all sorts of emotions about frequencies and energies and maybe even the shoe. Okay. But these e to the minus I, e sub I, h bar, again, times delta t, right? These are the eigenvalues of the time evolution operator, okay? And in fact, that is going to be a very general statement now. No matter what the dimensionality of the Hamiltonian system is, whether it's discrete or continuous, these things will still be the eigenvalues of the time evolution operator, even though here I'm writing them down for a finite and discrete sized Hilbert space. But I want you to see and to note at this point that we can't now say that this is equal to something times psi, right? Because each of the coefficients, or each of the probability amplitudes, if you like, is being multiplied by a different complex exponential. And so once I add time into the picture, I really have to worry about the fact that each of these states are evolving independently, right? And that could cause problems for us when I try to recombine that state later on. And again, we'll probably see some more of that in our problem set. So I want to talk about an example here. And I admittedly, we don't have a ton of examples to work from because we've only seen really one Hamiltonian so far. We've only seen one expression for an operator, and that is if I take a particle or an atom, or in this case a nucleus, and I put it in an external magnetic field, I can use the fact that the energy is minus mu dot B to turn it into a Hamiltonian operator, which says that the energy states of the system, or the energies of the system, are going to be measured by mu dot B. So I'm going to go ahead and put my magnetic field in the z direction. Again, this should all sound very familiar. And I can write down that my Hamiltonian then is proportional to the sz operator, right? And that's, of course, because I've chosen to put my magnetic field in the z direction. And, of course, I'm going to work in the sz basis because that's the basis that diagonalizes not just sc, but it diagonalizes the Hamiltonian operator. So if I write this out, I know that I have this big old complicated coefficient, minus gq over 2m h bar b naught times the matrix that goes from 3/2 to minus 3/2 if I'm in a spin 3/2 system. And so to just put that explicitly, right, that means that if I act h on the plus 3/2 z state, I get out this eigenvalue for the energy of the state, right? Now, your book, and many times, will take as many of these coefficients as possible and try to write them as something that's easier to write. And so I'm going to take the g, the q, the 2m, and the b naught. I'm going to make them something that we're going to call omega naught, just so that my states now look like omega naught times the eigenvector, or sorry, they look like omega naught times the eigenvalue of the sz operator. So if I want to evolve this state through time, well, I have to write down the time evolution operator, which is the exponentiated Hamiltonian, which, because it's diagonal, is something that I can calculate sort of explicitly, and I get down the diagonal all of the different eigenvalues of the time evolution operator, where each of the eigenvalues of the time evolution operator has in it the eigenvalues of the energy operator, which has in it the eigenvalues of the sz operator, right? But there are really 4 different eigenvalues of the time evolution operator that correspond to the 4 different energy states of the system. And so if I write this out, right, so I'm going to start with a state psi. It's going to be broken down into its 4 possible states. Each one of those has an unknown probability amplitude. I've actually made the decision to get rid of 2. I'm going to set 2 of them to 0 just because there's too much writing on the next page if I don't, right? Things get kind of complicated, right? But this is the state that I'm going to start in. There's going to be some part of it that's in the spin 3/2 state, and there's going to be some part of it that's in the spin minus 1/2 state. And now I'm going to say, let's move that forward in time by some delta t, which means that I add, right, I multiply by the time evolution operator, and the 3/2 state picks up the eigenvalue of the 3/2 state for the time evolution operator, and the 1/2 state picks up the eigenvalue of the 1/2 state. And so these 2 states now have some, they have some time dependence to them, right? They have an exponential in front of it that tells me how this state is going to actually evolve through time. And of course, because I knew this was a unitary operator, I know that that at some later time, my state is still going to be normalized, right? And in fact, when you look at this and you say, well, Tom, these kind of look like phases, right? So if I tried to measure this later, at least if I tried to measure the spin of this state in the z direction later, it doesn't look like the probabilities would change very much. And that's true, although the probability amplitudes have changed. which means that if I am trying to measure it in some other basis, right, or if rather than try to measure it in the sz direction, if I try to measure the state, say, in the sx direction, then the measurements of those operators, so the measurements of all of the operators that don't commute with h, are going to be time dependent, right? And this leads us to lots and lots of cool physics, and we'll get to talk about that over the course of the next week. Okay. All right. So, what do I want you to know for today? One, the Schrodinger equation is a time-dependent equation. It tells me how states evolve through time, and the big meaning of that is that each of the eigenstates of the Hamiltonian, each of the eigenstates of the energy operator, has its own eigenvalue of the time evolution operator, which tells me how to advance that state through time. And since the time evolution operator and the Hamiltonian commute, the eigenstates of h are the eigenstates of t, right? And if I'm in some energy state with energy E sub n, then the eigenvalue of the time evolution operator for that state is given by e to the minus I over h bar E sub n delta t, right? That tells me how each one of those states commutes. Okay, so this was sort of a brief introduction to what is the Schrodinger equation and how might we use it. We're going to have to do a couple of examples before it starts to make sense. But I really never want you to forget that the Schrodinger equation itself is really the statement that the Hamiltonian generates translation through time.